Greetings, Spartans. Today's lesson is section 3.5, derivatives of trig functions. This will be one of two videos for the section. This one's going to focus more on just derivatives of sine, cosine, tangent, cosecant, secant, and cotangent. And the next video will focus more on word problems. Make sure you have your calculator. I'll be using it extensively in this lesson. And make sure you're in radians, which you probably are from previous homeworks. So I have a sine curve drawn, and if I want to find the derivative of sine, remember the derivative is the slope of the tangent line at some point along the curve. So you probably can't see, but I already have a few points plotted. I like to start where is the slope 0? In other words, where is the tangent line horizontal? And the tangent line is horizontal at pi over 2. Slope is 0, so pi over 2, the slope is 0. And then it's also 0 at 3 pi over 2. Horizontal tangent here at 3 pi over 2, if you were to draw it in, the slope would be 0. So now the question is what's happening in all these other intervals. So I'm going to start when theta is 0, Okay, so when theta is 0, I have a pretty steep slope for my tangent line. So my ruler here is representing the lines. And as I approach pi over 2, the slope is still positive, but that slope is approaching 0. So my slope is still positive, but it's approaching 0. Let's look at pi over 2 to pi. So from pi over 2 to pi, so here I am at pi over 2, the slope is 0. So what's happening is my slope is negative, 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 and it's a larger negative number as I'm going down. Oh, that's not such a very good curve. And then from pi to 3 pi over 2, so from pi to 3 pi over 2, my slope is still negative, but it is approaching 0. And I bet you can figure out what messed up curve this looks like on my paper. So at 3 pi over 2, so from 3 pi over 2 to 2 pi, I'm starting with the slope of 0, and then I'm moving in the positive, 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 positive direction. And that slope is increasing. I think of it as like walking up a hill. Oh yeah, I can walk. Oh, I better, start working out more so I can climb up this hill. And there is your really awful cosine curve. If I was in the classroom, I'd erase it with my whiteboard marker. I guess I can use my erasable pen, but I won't prolong the pain any longer. Okay, so now I've got a cosine curve. Here's my parent cosine. Okay, when theta is 0, the tangent is horizontal, so 0, 0. When theta is pi, the tangent is horizontal, the slope is 1. Remember, this graph represents the derivative, which represents the slope. It's not a cosine curve, it's the derivative of the cosine curve. Which I'm not gonna lie, that took me a long time when I was first learning how to do derivatives, like way back in the, ancient times. Okay, so from 0 to pi over 2, from 0 to pi over 2. So I'm starting at a horizontal tangent line, and I'm going to a steep, 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 steep negative slope. From pi over 2 to pi, so from pi over 2 to pi, my slopes are still negative. Remember, my ruler represents the tangent line. My slope is still negative, but it's approaching 0. Can you figure out what graph this looks like? Okay, and then from pi to 3 pi over 2, so from pi to 3 pi over 2, I'm at 0, my slope is 0, and then I'm increasing in the positive direction. Hey, not too bad. I'm actually kind of impressed with myself. Then from, you can't see, I'm totally laughing at me. All right, anyway, from 3 pi over 2 to 2 pi. So from 3 pi over 2 to 2 pi, the slope is positive, but it's leveling off and approaching 0. Oh, see, spoke too soon, I missed it. The derivative of cosine is negative sine. Okay, I'm gonna do one proof. Let me adjust this here a little bit so you can see. Let me try and zoom in a little. Okay, so I'm gonna do the proof of the derivative of tangent. Okay, so here we go. I'm going to rewrite tangent as sine over cosine, and I'm going to do this because I think that's distracting. Okay, so this is going to be the derivative of sine over cosine. And then from here, I'm going to use the quotient rule. So the quotient rule, that would be the cosine times the derivative of sine, which we just did was cosine. You have to memorize them. There's no ifs, ands, or buts about it. You need to know that the derivative of sine is cosine and the derivative of cosine is negative sine. It's going to make your math life so much easier. Minus the numerator, which is sine, times the derivative of the denominator, and the derivative of cosine is negative sine, all over the denominator, which is cosine, squared. Okay, can you see where this is going? Cosine squared plus sine squared is 1. I'm not sure if I told you guys, if I told Algebra 2 honors, but that main identity, the Pythagorean identity of sine squared plus cosine squared is 1 is just like, that's it, gotta know it. So the derivative of the tangent is equal to 1 over cosine squared, which is also known as secant squared. Okay, page 145. Here they all are. You can copy them down from page 145. So I'm just going to do a few examples of taking derivatives of various binomials, trinomials, etc. that involve trig functions. I really recommend try to prove these. They're not that complex if you stick with tangent is sine over cosine, or cosecant is 1 over sine, etc. And then a lot of it is the quotient rule. So play around with it, see if you can get those. And I'd be happy to help you with some of them if you would like. Okay, here we go. So I want to find the derivative of 3x plus x times the tangent of x. And this is number something or other in the book. Okay, so the derivative of 3x is 3 plus, and then let's use the product rule. So for x tangent of x, the derivative of, so it's x times the derivative of tangent, and then plus tangent times the derivative of x. So here we go. You have x times the derivative of tangent, which we just did was secant squared x, plus tangent times the derivative of x. So tangent times the derivative of x is just tangent x. I don't know, you don't need these huge brackets. I have no idea why I drew them. So this looks like, this is it. You can't simplify it any further. We are done. So that's 3 plus x secant squared x plus tangent of x. And there you go. Okay, and then let's look at another one. Let's look at y is equal to the cosine of x over 1 plus sine of x. Okay, I'm going to use the quotient rule. So the quotient rule says, I forgot my notation. I'm going to find the derivative. So the derivative of this function I should have just erased it there. It would have been a lot nicer. Okay, so the denominator, 1 plus sine x, times the derivative of the numerator. And the derivative of the numerator is negative sine x. So I'm going to put the negative in front. Minus the denominator. Sorry, the numerator. I almost messed that one up. The numerator times the derivative of the denominator, which is cosine x. And that's all over 1 plus sine x quantity squared. All right, here we go. So I'm going to do a little bit of multiplying out here. So this becomes negative sine x. If you distribute, negative sine x minus sine squared x minus cosine squared x over 1 plus sine x squared. Okay, if you factor out a negative 1, so I'm going to skip some steps here, you're left with sine x, and then you're left with positive sine squared, positive cosine squared, which is indeed 1. Okay, so now you can reduce this. So sine x plus 1 reduces with 1 of the 1 plus sine x quantity squareds, and you get negative 1 over 1 plus sine x. Okay? Okay. So the last problem I'm going to do is, I think it's number 16, and it involves harmonic motion, I think. Yeah, this is number 16. This is the last one I'm going to do. And then we're going to play around with the calculator a little bit. Yeah, I told you, make sure you have it, and then I forgot to do a couple things, sorry. Okay, so number 16 says that you have a body moving in simple harmonic motion with a position function s is equal to f of t. Harmonic motion is like a yo-yo, a spring. Yo-yos are the first thing that come to my mind. And we want to find velocity, speed, acceleration. Then we're going to evaluate at a specific time. So the position function that I am given is equal to the cosine of t minus 3 times the sine of t. Okay, that was given. So the first question is velocity, speed, acceleration. Okay, so velocity is the derivative of position. Velocity is the derivative of position. Okay, so derivative of cosine is negative sine. The derivative of sine is cosine. So this becomes minus 3 cosine t. So a little side note, why isn't this just -3, right? Isn't the sine of t a variable? It's not. The sine of t is a function. X is a variable. So let me just show you a quick little side note. How do you know? You can use the product rule and it'll come out pretty nicely, pretty quick. Okay, so -3 sine t. So this is a side note. How do you know that the derivative of -3 sine t is -3 cosine t? So -3 sine of t. You know what, let me use a darker color. Okay, so product rule. This is -3 times the derivative of sine, which is cosine. Product rule. The first times the derivative of the second, so -3 cosine t, plus the second, which is sine t, times the derivative of a -3, which is 0. And so that's why you end up with -3 cosine t. So this is a function. Cosine is a function. X is a variable. So this isn't just, you can say that the derivative of -3 sine is -3. Okay, so it's -3 cosine. All right, well, there's my position function. That's it. Done. Velocity, I'm sorry, they ask you for the speed. So the speed is the absolute value of the the velocity. That's kind of hard to figure out without the absolute value of the velocity is difficult to figure out if we don't have values for t. So we just very simply say that the speed is the absolute value of -sine t minus 3 cosine t. That's it. And then the next thing they ask for is acceleration. So the acceleration a of t is the derivative of the velocity v of t. Okay, so I'm just gonna I can do it up here. So you have -3 sine t. The derivative of sine is cosine. So you get negative cosine t. And then the derivative of cosine is negative sine. So times -3 is plus 3 sine t. Okay, and there is my acceleration. Okay, let's do the evaluations of, they ask you to find the values at pi/4, and then I'm going to do all the calculator stuff at once. So, given that t is pi/4, here we go. Let's plug in. This is a straight plug and chug. So I'm going to have, when you plug in pi/4, you get that the velocity, which you can do on your own, is -2√2. So this is the velocity. The speed is +2√2. Speed is the absolute value of the velocity. And then the acceleration, again, just plug in pi/4 to the acceleration function, do some evaluating, and you get √2. So do the plugging in just to make sure that you're not making any careless mistakes. Pi/4 is nice because all the sines and cosines are a variation of √2/2, so that's good. Okay, I'm going to use the calculator now. I already have a lot of things plugged in, so you should hit pause and you should plug in the velocity. Start with position. Plug in the position, plug in the speed, velocity. I'm sorry, let's try again. Plug in position, velocity, and acceleration into your calculator. Okay, so push pause until you've got that going on. Okay, and then you graph all three, and that is super hard to see. That doesn't make it any better. Sorry, I'm messing around with it. Okay, that's better. I think it's better at least. So the first curve is position. The second curve in my graph is red. That's velocity, which is the slope of the tangents, and then acceleration. It looks very pretty. So that's what the three look like. I want you to make note. Turn off your velocity function. You can ignore all this up here. Turn off your velocity function. What do you notice about cosine x, negative cosine x, negative 3 sine, positive 3 sine? The position function and the acceleration function, they're reflections of each other. So if you turn off velocity, you'll see that you get a reflection. My graph is pretty slow. Again, another very pretty picture. Okay. So this is just a graphical representation of the problem with the harmonic motion. Okay. We're going to go back to the very beginning. My apologies, I forgot to do the proofs, not the proofs, the graphical representations of sine and cosine. So I am going to review how to plug in the derivative. So let me clear that out. Hold on. Okay. So you have sine x. So I'm going back to the very beginning. We did the sine of x, and then we found that the derivative was cosine of x. Okay, so just a reminder how to find the derivative keys on your calculator. Math, N-D-E-R-I-V. Your book says N-numer, I think, something like that. So it's the derivative function. All right, and it automatically shows up as such, x. Okay, two ways you can do this. I just typed in sine, but another way to do this is alpha, trace. So now what you are doing is you are telling the calculator, find the derivative of the function that is plugged into y1. You're just telling the calculator, find the derivative of the function that's already entered into y1. And then x equals x. Okay, I'm going to turn my sine function on because my sine function is off. So here's my sine curve. And there is my derivative. Does your derivative graph really slow? My derivatives graph really slow compared to the like the regular function, so to speak. And you can see that the derivative of sine is indeed cosine. All right, and then let's check that out for, let me turn these off. Let's check those out for cosine. So type in cosine of x. And I want to find the derivative of cosine, which we showed was negative sine. But let's just see what that looks like on the calculator and get some practice using the derivative keys. Math, derivative, which is number 8. So you're finding the derivative of the function with respect to x. So now when you do alpha trace, I want the calculator to find the derivative of the function that's listed in y sub 3. So I'm going to do alpha trace, and I'm going to choose y sub 3. And there's my cosine curve. And then here comes my derivative, which is a negative or a reflected sine curve. I like reflected better than negative. All right, so I didn't use a calculator as much as I thought, sorry. But it is good, just practice, especially like on that word problem I did. On this one, you know, plug them in, you can't even see that. Okay, so there will be another lesson on 3.5, which will deal more with applications. If you have questions, post them on Classroom. Have a good one.